So this is an example. So what you see here is an example of what is called, so this is an RC, so let me write it here. So this is an RC circuits. So an RC circuit has a power supply. It has a resistor. Capacitor. Then it also has a switch. Now the power supply is called the charging. So the very first thing that we're going to do is that going from, so this is figure number A, this is figure number B. So going from point A to point B, we're going to close the switch at point A. All right, so when the switch is connected here, then it means that the current is going to flow like that. So it means that the C and the R are in series. So this is called the charging. So this is the charging. Now, when this capacitor is 100% charged, then you're going to remove the switch from here and place it at point B so that no power supply is coming in. And so what is happening is that the capacitor is just going to supply energy to power this resistor. So this will be called discharge. So you have the charging circuit and the discharging circuit. It just depends on where you place the switch. So in one of the examples, you want the switch to be connected in such a way that the body is supplying energy to charge the capacitor, right? But once the capacitor is 100% charged, you cannot charge it beyond 100%. So now you want to use that capacitor to supply energy to a resistor. If you think about it, this could be something like a light bulb, right? So now the capacitor is just losing energy and supplying that energy to a light bulb. And the light bulb is just going to, it's called I square R. This is just, so this energy is just going to show up as heat. Nothing, is just heat.
So the light bulb would technically still would illuminate until the capacitor runs out of energy?
Right.
Okay.
Yeah. And that's a very good question because as I'm going to show you, the current is going to look something like that, right? So as the capacitor is losing energy, the current is, so if this was something that you do in the lab, you're going to notice that at T equals to 0, the light bulb is going to be very bright, right? But then it's going to eventually just slow down and die out and gets dimmer and dimmer. And how long is going to take, so for example, how long does it take for the brightness to go to 0? It depends on something. It depends on what I'm using as for the resistor, and it also depends on the value of the capacitance, right? So as a matter of fact, R times C is called the time constant. And that tells me how long the capacitor can power the light bulb. So for example, if the time constant is very large, and this is what you need, for example, in a cell phone, right? So for example, you want to charge your cell phone for a longer period of time. So you need a higher time constant, right? But if the time constant was just something like 5 minutes, it means that you can charge and discharge and lose all the energy within a very short period of time. All right, so let's look at this charging. So again, as I said, when you're charging a capacitor, if you look at this, so right now, just remove all of this. This is not playing any role, right? Because the switch is connected to point A, so the current is flowing in this direction like that. Now, this is just like a single, again, we're going to look at this as a single loop. So this is just a single loop. And so we can apply, so this is called, we can apply the Kirchhoff's rule. So if I go in this, so call this point A, point B, point C, point D. So as you go in this direction like that, if you write down all the change in the voltages, you're going to see that you have, so let's say there's some amount of current here, I, that is flowing. Now so this term, so remember that the charge so at any time, the charge in the capacitor is given by this equation here. So it means that the voltage across the capacitor is Q over C. That's why you see this value right there is Q over C. Now we know that the current, so remember that current I is the rate of change of charge with respect to time. So it means that if you go in here in place of current, you substitute this, you can rearrange this equation and write this equation like this. Now, this type of equation here is called a differential equation. So basically, you can solve this equation by doing a separation of variables here. So you rearrange the equation in such a way that you have the Q on one side and you have the T on the other side. Then you can go ahead and integrate both sides. And when you take that integral, I don't know if you guys have seen something like this. Are you guys in Calc 2? Calculus 2?
Yeah.
Have you guys seen something like anything on differential equations yet? Some basic differential equations. So if you think about, let me just share my screen here for a second. Just to kind of review. So differential equation. This is almost like, if you think about it, it's just like saying that it's the opposite of the derivative. So for example, you can think about it as the anti. Now that's right. So suppose that you have an equation that looks like this. So what function is it such that when you take the derivative of that function with respect to x, it gives you x? So you can see that I'm taking that's why I said that the differential equation is almost like the opposite of the derivative, right? So remember that if I give you any function, for example, x to the power 10, you can calculate the derivative, right? You just take dx by d by d. So x to the power 10 becomes 10x to the 9. So now we're trying to solve the problem in the opposite direction. So now I'm saying that what function is it such that if you take the derivative of that function, it gives you x?
1/2 x squared.
1/2 x squared, that's correct. So f, right? And so I can say that this is a solution to this differential equation right here. Why? Because if you take the derivative of f with respect to x, you get x. Now you can also think about other examples. You know, for example, let's say example. Right. Then in this case, you know that, for example, f is going to just be sine of x, because the derivative of sine of x is cosine of x. Now, sometimes you can have something that looks like this. Let's say dy by dx. So what function is this such that if you take the first derivative of that function with respect to x, the answer is going to be x times that function. When you have something like this, it's a little bit complicated to guess what the function is. So the way you're going to do this is that you're going to use a method that is called separation of variables. So you write this as dy over y is equals to x dx, like that. And then you go ahead and integrate both sides. When you integrate dy over y, what do you get? It's natural log. So you get something like the natural log of y is equals to, let's say, x squared over 2. And then solving this equation, you get y is equals to e to the power x. Now, let's see, let's see something here. So this is what we started with, this equation here, dy by dx is equals to x times y. And we've just shown that y equals to e to the power x squared over 2 is the solution. Now let's double check to make sure that this is the case. If I gave you this function and I asked you to find the derivative of that function, how would you do that? You can use chain rule. You say let u be equals to x squared over 2. Then dy by dx is equals to dy by du times du. Right? Now, what is dy by du? Dy by du is just d by du of e to the power u, which is the same as e to the power u. Because the derivative of e to the power x is the same as e to the power x. Right? So notice that this is just going to be equals to e to the power u times du by dx, which is just x. And again, this is just e to the power x squared over 2 times x. Now again, you see that this is the same as y times x. All right. So this is just a kind of like a review because we need that when we solve this equation here. So I'm going to go back to my PowerPoint. So let's stop share here, then I want to share this. Sharing the right side. Okay, so share this. All right. So as I said, if you integrate this equation here, this is what you're going to end up with here. So you get, so you want to integrate this from 0 to q. And if so again, this will just give you the natural log. And then if you rearrange that, you get this equation for q. This equation for